Number systems is a fascinating topic. Throughout human history, different cultures have come up with different ways to represent numbers and to actually deal with arithmetic. The system that we have settled on in the modern world as humans is Hindu-Arabic system. Notice that that's not actually the case for computers. They will operate on a different number system than we do when we do normal everyday arithmetic, and that is something we're going to talk about a little bit later. Other interesting number systems that you should explore if you're interested in the subject are Egyptian, Babylonian, ancient systems of Mayans and Incas are fascinating different ways to actually do mathematics that resulted in different developments of mathematics in all of those cultures. The system that we use today, the Hindu-Arabic system, was developed around 800 BC and didn't actually necessarily immediately permeate the world because, well, for one thing, travel wasn't really that easy at that time. The system, as we know, it uses 10 digits and powers of 10. Now, that is likely due to the fact that, well, we have altogether 5 fingers in our hands that are, in fact, sometimes called digits. The system is positional. Where every digit is determines how sort of important it is, in a sense. And so we are going to take a quick look at how our system works, because that's something that we're used to working with all the time, before we dive into other systems so that we can draw an intuition about the numbers as we have known them since childhood. 4,235. If I were to write out what that means, and in fact, for example, how English states this in words, I would say that it's altogether 4,235. So notice that the way I expand this number goes the way we write it from left to right, but really it actually works from right to left. The importance or the real value of this 4 is determined by the fact that it's where it is in the sequence, and therefore it's thousands and not, for example, millions. Now, I already said that the system uses powers of 10, and that can be visible in what actually happens to the values attached to each of the digits. So the other way to rewrite this would be 10 cubed, 10 squared, 10 to power 1, and finally 10 to power 0, which is just 1. So this is what we call units, and then we're going to have tens, hundreds, and thousands. So we start from the right. The rightmost number will correspond to the degree of 10 being 0. The next number will have degree of 10 as 1, the next number over as 2, and the final number in this case as 3. Notice that this is a sort of small enough number that we deal with fairly often, so just one glance at it, and I know it's going to be in the thousands. But if there were a bunch of digits, then you actually would have to go from the right, and sometimes we also separate them with periods for this exact reason, going from the right to the left, so we would know whether we're talking about millions or trillions or just tens of thousands. If you do have a decimal, it actually works in the exact same fashion as before, but to the left of the decimal, our powers increase, and to the right, as we go to the right, they decrease. So just as before, the units here correspond to the power of 10 being 0, and then they increase going up on the left, and on the right, they decrease. So what's the power in the negative direction after 0? It's going to be -1, and that's exactly what we have here. And this 5 corresponds to 10 to the power of -2. So if I were to write 42.35 in the expanded form, I would get 4 tenths plus 2 units plus 3 of the 1/10 plus 5 of the 100ths. If I am to write these out as fractions, that's in fact exactly what they are. This is 1 over 10, and this is 1 over 100, which is 10 to the 2. Any positive integer in the system can be written uniquely as a sum of these types of products. For the powers that are also themselves integers. Now I'm talking about positive integers. We are not going to work with fractions, so we're going to focus on integers, but I wanted to show you here that the system actually works exactly the same way for integers as it does past the decimal point in the other direction. 10 is what the base is in the system, and again, likely due to the fact that humans have 10 fingers, although some of the ancient systems actually work with 20 as the base. Because if you think of it, we have 20 fingers between our hands and feet, so that also seems like a reasonable base to use. The way that our system works can be explored with various what are called manipulatives. So for example, you can actually pretend that this is a real board with real chips, and then we can think about how would we actually turn this into a number that is represented within our system. For the number of hundreds here, we have 3. For the number of tens, we have 4. For the number of units, I'll actually have to go through and count. I can't capture the number with just my eyes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 units. So the number that I have, is it 313? Well, it doesn't quite work like that, right? Once we get past 9 in any one of these categories, we have to actually transfer some of the numbers into the upper category. So what I'm going to have to do here is take 10 of these units and turn them into 1/10 here. I'm going to transfer 10 of these guys over, increase the number of tens by 1, and decrease the number of units by 10. So overall, the number that I have is 353. So let's write this out. The way that I originally counted it, it was 3 hundreds, 4 tens, and 13 units. So far, there is nothing wrong with it, because I, in fact, do have all of the numbers written in the form of a number times the power of 10. But the problem is, if I am to use our positional system, each one of these coefficients in front of the powers of 10 has to be less than 10. The moment I have something greater than 10, the problem arises. Because if I were to write it like this, it would no longer be read as 300 4 tens and 13. It would be read as 3,413, which is of course not the same as is stated here. So that is not right. In order for me to fix it, I have to transfer the number of units that is bigger than 10 into the higher register. And once I do that, I end up with 300, 5 tens, and 3 units. Now that I have that, all of my coefficients are strictly less than 10, and so the number as represented in our system is 353. This might seem elementary, but again, that's only the case because you've been working with the system since you were little kids. This is going to become a lot less intuitive when we switch bases from 10 to something else, but we're just building our recognition of these patterns in the system we're familiar with before we work with something that will appear more complicated but have the exact same underlying structure. So to answer the second question here, what is the most number of stars we can have in any one column? It is, of course, 9. The moment we hit 10 as a number is the moment we cannot write it in one position in our system, and that means that we're going to have to transfer it up. The other really useful manipulative that kids use actually in kindergarten when they learn the system, because although you're familiar with it, little kids are not, and it seems as unintuitive as any other system that would be taught. The manipulative is called Dianese blocks, and they are physical beads and blocks consisting of these beads to highlight the relationship between the different powers of the numbers. So we have a unit, and that represents, just like above, the actual units. Then we can put these little units together to form tens, or what they're called longs. So once I have 10 units, I have myself a long. Then I can put the longs together, stack them up, and once I have 10 of them, I have a flat. I can stack these behind each other in this fashion, and once I have 10 of them, I have a block. So in our system, this will correspond to units or just ones. Longs will correspond to tens, flats will correspond to 100s, and blocks will correspond to 1000s. Because of the way that we compose these together, I cannot draw a four-dimensional cube, and so we stop there. But of course, this is again how you figure out that that's how the system works. In base 10, it's easy because we're used to dealing with it. But once we have to start thinking about what that looks like in base 5, things get a little bit more interesting. What would the blocks look like if instead of base 10, we decided to write everything down in terms of powers of 5? Well, this was the picture of the blocks for 10. So for 5, we're going to have a unit. A lon will then consist of 5 little units together. A flat will be a 5 by 5 square. And then a block will be a corresponding three-dimensional extension of that. What does that mean in terms of the digits that are used in the system? Well, notice that when I move from a unit to the long, I have a new structure. So I no longer have 5 separate units, I already have one long. So the moment I glue 5 of these guys together, they're no longer separate units, they become this new one thing. The moment I take 5 flats together is when 5 longs together is when I get one big flat. So at most, I can have 4 of these separate. The moment I have 5 of them, I have a new structure. It's the same thing here. I can at most have 4 longs separately. The moment I have 5, they get glued together in one flat. So in terms of digits, I can have 0, I can have 1, 2, 3, and 4. The moment I have 5 is when I have to move to the higher dimension. In terms of the decimal system here, of course, the digits are going to be very similar, strictly less than 10. 0, 1, 2, all the way up to 9. Because the moment I glue 10 units together, I'm going to get the long. The moment I glue 10 of these together, I'm going to get a new flat. But I can have 9 of these separately and not yet have a new higher structure. Now, what if I actually have now a number written in base 5? So bases usually appear as subscript, either written down in letters or just as a number. So for example, 3 with a subscript of 5 will indicate that I'm talking about 3 in base 5. This is where our familiarity with our system will actually help us as an analogy. Remember how we've distributed the powers of 10 through the decimal number? Well, that's the exact same way we're now going to distribute powers of 5 through the number in the base of 5. So I'm going to go from right to left, and I'm going to assign powers of 5 to these digits from 0 and up. So 5 to 0, 5 to 1, 5 to 2. So in this particular case, I'm going to then take the actual digit and multiply it by the corresponding power. So I have 1 times 5 squared plus 3 times 5 to power 1 plus 2 times 5 to power 0. So again, the way that we read off the numbers is going to be just the actual coefficients, and that's where we get 1, 3, 2 as the number. And the powers of 5 decrease from left to right. So if you actually were to now expand it and compute it, you're going to get, I believe, 42, and that's going to be in the decimal system. So 135 in base 5 is the same as 42 in base 10. And you can proceed the exact same way through the rest of the examples. So I encourage you to pause the video and actually do that before coming back and watching me go through the rest of them together. Okay, so the reason I didn't do this one first is because sometimes it gets a little bit confusing. There's only one digit, but remember, when you're working from right to left, the rightmost digit gets the power of 0 assigned to it. And here, there's just nowhere to proceed. So we're done right there. So it's going to be 3 times 5 to power 0. Anything to power 0 is just 1. So this is just 3 in the decimal. 3 in base 5 is the same as 3 in base 10. And that's pretty obvious here. 3 of the units in both bases are just going to be 3 separate units because it's not enough yet to move up to a new register in either of the system. 14, so this will be power 0 and this will be power 1. So overall, I'm going to have 1 5s plus 4 of these units. So computing them all together, I'm going to have 5 plus 4 is 9 in base 10. Zeros are dealt with just like any other digit, so don't forget to include them in your powers though, because otherwise you're going to get something a little bit out of whack if you just skip the zeros. You have to, of course, involve them on your calculations just like any other number. Don't discriminate against zeros. So I'm going to have 1 times 5 cubed plus 0 times 5 squared plus 0 times 5 to power 1 plus 4 times 5 to power 0. Whatever number that happens to be. Now, notice, of course, I didn't have to write these out because 0 times anything is just 0. But I am writing this down so we can see that these are exactly the digits in my original number. That is, in fact, how digits get used in the positional system. Okay? One small interesting pattern that we can already notice here is, I believe that this is 129. Comparing the numbers in base 10 versus the numbers in base 5, purely for size, we notice that the numbers in base 5 tend to be longer. And that makes perfect sense because in base 5, I'm going to switch to the next power after 4 steps. The minute I hit 5th step, I have to actually increase to the next power. Whereas in base 10, I have to do this only after 9 steps. So this allows me to grow my numbers a lot more in the same position in base 10 as it does in base 5. So as a general rule of thumb, smaller base will mean longer numbers. As many of you are probably aware, computers don't use decimal systems, they use binary system. Bi means 2, so that is what the base is. We have powers of 2, and the digits are 0 and 1. I only have 2 digits to work with here. The reason computers use that is because these are easy to represent in a current. 0 represents no current, 1 represents actual current going through. So these are easier to program with in terms of the actual hardware, if you think of the microchips. Now, the way that we convert numbers to the binary system and from the binary system, again, is the exact same as for the decimal. So our previous understanding of the decimal system will help us here in the exact same way. Let's take a look at this as a binary number. Again, with the decimals, we start from the right with the power of 10, to power 0, and then move over to the left, increasing the power. Since this is now base 2, we're going to move from right to left, assigning powers of 2 that increase 1 at a time. And then once we reach the final number, we can write the whole thing out. So all together here, I will have, minding the coefficients, I have 1 times 2 to the 4th plus 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to power 1 plus 1 times 2 to power 0. And once again, let me highlight these coefficients here because they are exactly the thing that forms the actual number. Right? It's not, the powers of 2 correspond to the value, the coefficients correspond to the sort of digits of the representation. Now, after I have written it out like this, I can, of course, compute all of this together, and this will turn out to be, I believe, 27. So once again, the conclusion that we reached in terms of the pattern on the previous page is that the smaller the base in the system, the longer the numbers, is certainly true in this case as well. The decimal number 27, so 2 digits, corresponds to a 5-digit number in base 2. Every time I have to up the number in the register here, I can only go up to 1, and then I have to move to the next one over. So I don't have nearly as much freedom here as I did within the decimal. So let's see how we actually, let's say, increase the numbers in either system. In the decimal, going from 1 to 10, we notice that for the first little while, we simply increase the units digit until we can no longer do so. The moment we hit the 9, we can no longer increase the actual digit itself, and we have to introduce the new spot. This new spot will get an additional unit, and the units themselves will decrease all the way down to 0. So think about how this goes through, let's say, the teens. So we get 17, 18, we keep increasing the rightmost number until we can no longer do so. Once we hit the 9, which is the highest available digit, we're going to have to do something different. We're going to have to up the number of tens and completely diminish the number of available units. So I will add 1 to the number of tens, making it 0, and I will annihilate 9 all the way down to 0, starting that count from scratch. And then again, I will persevere until I get 9 as my units. Being unable to increase this anymore, I will up the next available number by 1 and change up my 9 for 0. The change will happen a lot more often in binary because the highest available digit I have is 1. So I will have to swap every single time I get a 1. 1 in the decimal is also 1 in the binary. So as per the same rule in the positional decimal system as in the positional binary, I will try to increase the rightmost number. But I can't go above 1 here, which means that I'm going to have to introduce a new register here. And remember what happens in the decimal? I add 1 to the new position, and I diminish the existing position all the way down to 0. So in the binary system, 2 is actually equal to 10. 1, 0. How do I increase that further? Remember that I am going to increase the rightmost position as far as possible. So here I can still do that. I can turn this 0 into a 1, and that is going to be my 3. Notice that you can double check this work because at any point I can go through and again think about what are the powers of 2 assigned to each one. I will see that it's 1 times 2 plus 1 times 2 to the 0, which will add up to 3. At the next step, I can no longer increase this 1. So I have to increase the next one over. But I can't increase this one either because I'm also out of digits here, which means I have to introduce the next digit. So for 4, I'm going to have to introduce a third digit and then completely wipe out the other 2. And carrying on in this fashion, next step, I'm going to try to change up the rightmost thing, which I can do in this case. For the next step, I can't increase this one, so that means that I have to increase the next digit over and wipe out the trailing one, and so on. So for example, for 7, I have 1, 1, 1, which I already know is going to be a problem because I cannot increase any one of them. So that means I have to introduce the yet new register, and so on. So swapping happens a lot more often, and by the time I get to 8, I already have 4 digits in binary to represent what I would represent by simply 1 digit in the decimal system. So yes, it seems a lot less economical in the number of actual digits, but it works very well, once again, in computer systems where 1 and 0 actually represent something in terms of electrical current. In terms of converting, we've already seen how to convert from the binary into the decimal. I simply write out the powers of 2 that correspond to each of the actual digits, and I proceed from there. Now, Once again, a reminder, you have to go from right to left because, for example, just staring at this will not tell me what power the first one corresponds to. So I will have to count it up all the way from the left. So what do I have here? 0, 1, 2, 3, 4, 5, 6. So this will correspond to 2 to power 6. So I have 1 times 2 to power 6, 1 times 2 to power 5, 0, 2 to power 4, and so on, all the way, as my number tells me, 0 times 2 to power 0. What about the other way around? What am I supposed to do if I have a decimal number and I would like to turn it into a binary number? The easiest way to do it is to find the highest power of 2 that fits within this number, look at the remainder, and repeat the process. Now, for those of you who are in computer science, you actually likely remember many of the powers of 2 offhand. But for those of us who do not constantly double things in their head, let me write out some of the first powers of 2. So we are just trying to figure out what is the highest power of 2 that will go over into my 209 here. 209, yep. And so I'm not quite there yet. 2 to power 5 is 32. But as any exponential, once it takes off, it starts growing fairly quickly. So once I hit 2 to power 8, I am actually at 256, which is already more than I need. So I can't use 2 to power 8, but I can use 2 to power 7, which is 128. So 209 is 128 plus, pull out your calculator, or you can do it in your head, 81. 128 is already a power of 2, so I don't need to do anything with this, but I need to further break 81 into powers of 2. So I'm going to look at what is the highest power of 2 that goes into 81, and I can see that it's got to be this 64 here. So 64, and what I have remaining of 81 is going to be 17. And again, I'm going to repeat this with the numbers in my line here that are not powers of 2 yet. So here it's 17. I'm going to look at my handy table-like thing here and look for the highest power of 2 that fits into that, which will be 16 plus 1. Now 1 is a power of 2 as well. In fact, 1 is always okay, so I'm essentially done. Now I'm going to write these as actual powers of 2. So 128 was 2 to power 7. 64 was 2 to power 6, 16 was 2 to power 4, and 1 is 2 to power 0. And now I have to write down the coefficients of all of these in order to form my binary number. Now watch out though, it's not going to be just 1, 1, 1, 1. Like that is not the answer. In fact, I know very well that that's not the answer because I'm already seeing that I'm going to be close to 1, 1, 1, 1. At 10, and this number is a lot larger than 10. I do have to account for all the powers that are missing. So I have 7, I have 6, but I don't have 5, which means that it is present there, but with a coefficient of 0. I then have 4, but no 3, 2, or 1, and those are all of the ones that I will actually have to write down. So the first one corresponds to power 7, next power 6, next power 5, which I don't have. Next is power 4, then power 3, 2, 1, and then finally the present power 0 here, right? So I have 4 terms here, which will correspond to 4 ones in my final answer, and we're then done. The way that we work arithmetically with binary numbers is once again exactly similar to the way we work with decimal numbers. We just have to make sure that we swap more often than with decimal numbers. So how did you learn addition in the actual decimal numbers? Let's say I'm going to have 34 plus 12. When we add numbers in a column, we go from right to left and present carries as they are necessary. 4 plus 2 is 6, 3 plus 1 is 4, and we're done. So if I had to, let's say, do 100 in binary, plus maybe 10, without any carries here, this is the simplest case, I would simply go from right to left, adding up in a column form. When I do have a carry, I'm going to have to do something slightly different. So what do I do in the decimal case? Let's say I start with the same 34, but now I add 18. What is going to change in my procedure? Well, when I add 4 and 8, I notice that it's 12, which is not something I can put in one position in my decimal system because 12 is more than 9, which is my highest available digit. So what I do write down is 2, and then I carry a 1 over into the next actual register. Once I do that, I'm going to add all the way down this column. 1 plus 3 plus 1 is 5, and that is what I write down here. Excellent. The exact same way is going to work in the binary. So let's say I have 101 plus 11. I add down a column. 1 plus 1 is 2, which I can't write down here because 2 is not a binary number. In fact, if we scroll all the way up, we'll remember that 2 is actually 10. 1, 0. So that means that instead of writing something down here, again, 2 is actually 10. This is where arithmetic is going to get a little bit confusing. So I'm going to write down the only digit I can write down and then carry over the 1 into the next position. Now, in the next position, I'm going to add all the way down the column. 1 plus 0 plus 1. And I'm in the same situation now again. I actually have a 2, which I can't write down, but 2 is equal to 1, 0. So I'm going to write down the 0 and carry 1 over into the next spot. Let's add this down now. 1 plus 1 is 2. Again, I can't write it down, but it is 1, 0. And that I can write down by introducing another dimension. So 101 plus 11 is 1000. Okay? As before, while decimal numbers are shorter, even the arithmetic operations tend to be a little bit shorter. I'm not going to talk about the subtraction because it works basically the exact same way, except for you have to borrow as opposed to carry. Now, I've already mentioned several times that the reason the binary arithmetic is actually useful is because we are able to implement it directly into the computers. So what if I wanted to design a circuit that takes two binary numbers and adds them together? If I simply have the binary numbers here, P and Q, how am I going to compute their sum? So let's first of all just fill in the table and then think about the circuit. So 0 plus 0 will produce a 0. 0 plus 1 will be a 1. 1 plus 0 is still a 1. But 1 plus 1, we've already just discovered, is 1, 0. So this is the one time that I introduce a carry and therefore have to introduce another digit. And this is how we're generally going to think of these numbers. The second part is going to represent the sum, and the first portion is going to represent the carry. Now notice that the carry in all of the other cases is 0, which will affect the arithmetic not at all. But now we're going to look at each column here separately. Thinking back to our truth tables where 0 is false and 1 is true, based on the truth values of P and Q here, what does this column represent? What operation gives you true only when both of the statements are true? This is an AND. So this carry is actually P and Q. The sum here is 0, 1, 1, 0. So if would have been an OR had this been a 1 and everything would have been fine, but that's of course now how the sum works. So what we have here is what is called an exclusive OR. So it acts as an OR in every other case except for 1 or 1 actually produces a 0. And we can also write that down as a logical sequence, although it's a lot more complicated than simply saying exclusive OR. It's P or Q, as an OR would be, but it's not P and Q. So we have to specifically exclude this one case. So this makes for a little bit of a complicated gate. Now, it is a fun exercise as a reminder of what the circuits look like to now actually construct yourself a binary combinatorial circuit with gates. You're going to need AND, OR, and NOT that would both produce the sum and the carry. So let's say you have inputs P and Q that go in, and you have a sum and a carry as an output. Give it a try, see what you can come up with. The next natural question to ask is, what do we do about negative numbers? We have introduced binary numbers. We understand that doing arithmetic on them is analogous to doing arithmetic as with the decimal system. But how do we represent negative binary numbers in the computer architecture where all we're allowed to do are using zeros and ones? For all of the examples throughout, we're going to think about working with an 8-bit system. This is just for the sake of an argument. It extends and generalizes to larger number of bits in the exact same way. So what we will think of having available is 8 spots for binary digits, 8 bits, and therefore the spots can only be occupied by a 0 and a 1. We cannot insert a negative sign. We will have to somehow represent negative numbers within this system differently than just using a minus. In order to do that, let's think of the concept of 2's complement. So again, while the definition is general for n, we're going to do examples in the 8-bit system. The 2's complement of a number x relative to a fixed bit length n is the binary representation of 2 to power n minus that number x. Let's work through an example and it will become a little bit easier to digest. Find 8-bit 2's complement of 27 is equivalent to asking for binary representation of the number that completes 27 to 2 to power 8. So binary representation of 2 to power 8 minus 27. Now that is something that we've just learned how to do on the previous page. So I'm going to start with 2 to power 8 minus 27 and first compute what it is actually in the decimal system, 229, and then start subtracting powers of 2, highest powers of 2 that fit into it, decompose the remaining portion, and continue until we can write everything out as a power of 2. So in this case, we're going to get 1, 1, 1, 0, 0, 1, 0, 1 in base 2. So this is the 8-bit 2's complement of 27. Again, complement means that 27 completes this number to 2 to the 8. The reason this is going to be useful is actually because of this inequality. We notice that the 2's complement of x will be between 2 to the 7 and 2 to the 8, because it will be 2 to the 8 minus the number, and if we're dealing with a number within a certain range, then we will always end up within this inequality. It's going to be bigger than 2 to the 7, because we're only subtracting at most 128, and it's certainly going to be less than 2 to the 8 because we're subtracting from 2 to the 8. Next is where we're really going to see how the system works. We're going to use the 2's complement to define 2-bit representation, 8-bit representation of x. And here's how we're going to define it. If x is already positive, then we're just going to take the direct binary representation of it. If x is negative, we're going to compute its 2's complement. The idea being, when you're computing 2's complement, the leading number is going to be a 1, and that is going to be the indicator that the number we're talking about is actually negative. If the leading digit is 0, then the number to begin with was positive. So we're using these 7 bits to represent the number, and we're using the leading bit to tell us whether it's positive, and therefore the leading bit will be 0, or negative, or the leading bit being 1. So let's take a look at this table that actually lists all the numbers between negative 128 and 127. So notice that for the number of bits, because I only have now 8 bits, but 7 of them being usable for a number, my possible integers will lie between 2 to the 7 and minus 2 to the 7, essentially, right? So for the leading 0, these numbers represent all the regular 8-bit representations of the corresponding number. Regular 8-bit representation. Leading 0 means the number is positive, and it's going to work like that all the way up to the 0 itself. Once we switch into negatives, the leading bit becomes 1, and this is where we're going to do a slightly different calculation, and instead of a regular 8-bit representation, we're going to look for 8-bit 2's complement of said number, which is, of course, listed in this third column here. So if we're looking at minus 1, we are going to compute the binary representation of 2 to the 8, minus 1. So minus 1, minus 1. Minus 2 will correspond to 2's complement of 2, and so on. Okay, let's see whether we can transfer it into computing the things ourselves. Find 8-bit representation of 51. Remember that the 8-bit representation for the positive number is just a binary representation, and for the negative number is 2's complement of that number. If we're asked to compute 8-bit representation of 51, 51 is already positive, so all we have to do is compute its own binary representation. So 51, let's note here, is positive, so we are simply going to break 51 up into the powers of 2 in order to compute its actual binary representation. So I'm going to have here 1, 1, 0, 0, 1, 1. So notice that this isn't an 8-bit representation yet because I actually only have 6 digits listed. But because I will be working within 8 positions for all the digits, this is the one time where I will have to write in leading zeros where necessary. What about 8-bit representation of minus 36? This number is negative, which means that instead of computing the binary representation directly, I am interested in computing the binary representation of its 2's complement. So 2 to the 8 minus 36. I'm going to skip the calculations here and just write down the answer. So in this case, it's going to be 1, 1, 0, 1, 1, 1, 0, 0. So notice that you can double check your answers for sanity. If the number is positive, remember that that corresponds to the leading bit being 0. If the number is negative, it corresponds to the leading bit being 1. If your answer does not follow this pattern, that means that you've done something wrong and you should probably redo your calculations. Now, interestingly, we can actually use this system too to compute a little bit more efficiently with the binary subtraction. Adding is always easier than subtracting. It seems that borrowing is harder than carrying. So what we can do is instead of subtracting, we will turn this problem into addition. So we're going to have, instead of 39 minus 25, we're going to write it as 39 plus negative 25, and then deal with the two numbers. So 39 in itself, we can convert to binary directly. It's already positive, so we're just going to write down its regular 8-bit representation. So in this case, it's going to be, I'm skipping calculations here, but it's going to be 1, 0, 0, 1, 0, 0, 1, 1, 1. And as for minus 25, because it's negative, we're going to compute its 2's complement. So 2 to the 8 minus 25. Again, skipping some calculations will result in 1, 1, 1, 0, 0, 1, 1, 1. And now we have ourselves an addition of these two numbers. So we will take them as our last step and simply add together in a column. Again, because carrying seems to be easier than borrowing, this is going to be an easy procedure. Also, remembering, for example, that on the previous page, we already came up with the actual circuit for the sum, we don't need to reinvent anything new. We can use this operation and therefore this circuit to now perform not just the addition, but also the subtraction of the numbers when defined using the 2 bits complement. Another system that is pretty prevalent in computer science and other areas of computational mathematics is hexadecimal system. Hex means 16, so this is a base 16 system. Now, we've already talked about how the lower the base, the more digits we're going to have to use. So this is essentially batting that exact problem. We're going to use a larger base, which means that our numbers are going to be shorter, and the bigger the base, the easier it is to represent large numbers in general. Now, if it is a base 16 system, that means that we're going to have ourselves more than the digits that we already have present in our decimal system. Now, of course, we can develop a whole new system of symbols for it, but we're going to reuse the ones that we have and add the additional one in forms of letters. So base 16 system means we need 16 digits starting from 0. So from 0 to 9 is going to be ordinary, and then we're going to need 6 more that we represent by capital A, B, C, D, and F. So essentially this stands for 10, 11, 12, 13, 14, 15, but we would like to be able to write such things, so for example 15, in the one single space, therefore replacing it with the letter F. The way that this system works will be exactly the same as other based systems, except for now we're just going to have to get familiar with writing letters in positions of digits. So A7E, again, we start from the right, and we're going to assign powers of 16 to every position, starting from 0 on the right and working up. 16 to power 0, 16 to power 1, 16 to power 2. So altogether we have A7E in the hexadecimal system equals to the letter A. Now here we're going to have to think of what it actually represents as a number. So maybe let me write these out here explicitly. I could write A times 16 squared, but if I am going to have this expression fully in the decimal system, I can no longer have letters representing numbers. So 10 times 16 squared plus the next digit was 7, so 7 times 16 to power 1 plus E, which according to my numbering here is 14 times 16 to power 0. Okay, so once again, this 10 represents A, 7 is of course itself, and 14 is E, which is where we get A7E for the number. Whatever this comes out to be is going to be now in the actual decimal system. Okay, so this is how we go from the hexadecimal to a decimal. How do we go, let's say, from a hexadecimal into a binary? If these are systems used by computers, we probably want to be able to convert from one system to another. And there's a couple of different ways you can do that. For example, one way is to basically utilize this example, is to say we're going to go from the hexadecimal into the decimal and then into the binary. In this process, we already know how to do both steps, but it does seem to be a little bit inefficient to go through a decimal system. I am going to record it as a potential method because there's nothing really wrong with it at all. But maybe there is another way to do it a little bit more directly. So what about other methods? Let's say we're going to think about how this number is actually composed. B9F in the hexadecimal system. Let's look at what it is in the decimal, but only in terms of notation. So B is the number 11 in the decimal system. So I'm not converting the entire B9F, I'm only converting place by place value. 9 is of course just 9, and F is 15 in base 10. And I can actually work with each one of these numbers separately by converting them into the binary system. So I'm going to convert the number 11 into the binary. Just the number 11 itself, and that's going to be 1011 in the binary. Number 9 in the binary is 1001. And number 15 in the binary is 1111. And the way that we now put them together is quite literally by simply gluing them all together in the same time. So the B9F in the hexadecimal system is actually, we're just going to read off all the binary numbers here, is 1011, 1001, 1111 in the binary. Now, it's not going to work like that with any single system you introduce. So, for example, if we're moving this into the base 5 system, we couldn't actually quite do that. This works because 16 is also a power of 2. So 16 itself is 2 to the 4th, which means that we can think of these as 4 tuples of the binary numbers. And that is why we can move sort of directly into the base 2 without having to go through the intermediary of actually representing the whole number, but rather switching it into the letter or digit by digit format. Okay, so don't try it with any system that you're ever given. You can only do it with systems that have a base as a power of 2. Now, we're going to look at one more system just again to practice our understanding of what it means to have a base. And for that, I'm going to introduce you real quickly to a Mayan numeration system. This will slightly challenge your definition of how the actual placement systems work. Mayans used this system dating as far back as 900 AD, AD meaning before year 0. So this is negative 900. Similarly to, for example, cultures such as Egyptians, Mayan had 2 systems. One's for decorating, very beautiful symbols, very intricate, and one very simple for practical purposes. We're going to look at the practical system that they used for their calculations. It only has 3 symbols. It's a dot for 1, a bar for 5, and a shell for 0. Now, their system is a place-based system, so where a symbol occurs still determines how what value it actually has. 4 in the hundredths spot is not the same as 4 in the millionths spot, but they write their numbers vertically, from bottom being the lowest to the top being the highest. The base is 20. So here, the lowest row will represent 20 to power 0. The next one will have power 1, and so on, as far as we need to go, as long as there's symbols present. So, and now we write it out in the exact same way that we wrote out all of the other systems that we've talked about today, just thinking about what the symbols actually represent. 1 dot means 1, so this will correspond to 1 times 20 cubed, and then we add all the way down. A bar is 5 and a dot is 1, so altogether this is 6. So the system is also additive in that sense. If we put the symbols together, for example, 2 bars will represent 10. A shell means 0. So I know I don't have to write this out because this will not add anything to the sum. I'm going to just for the sake of completeness. And the last one is 3 times 20 to power 0. Notice that Mayan's base of 20 is even higher than the hexadecimal 16, which means that they were able to represent larger numbers with fewer symbols. And given the number of astronomical computations they performed, this was a very useful thing for their purposes. What about this number here? Following the same structure, I'm going to have that this symbol corresponds to the power 0, this one corresponds to power 1, this one corresponds to power 2. So together I have 5 times 20 squared plus 0 times 20 to power 1 plus, and again, it's additive, so 2 bars is 10 and 3 dots is 3. So altogether we have 13, 20 to power 0. It's a really neat system when you think about that. And the other thing that maybe doesn't come across as something inventive and quite deep and meaningful is the fact that they're one of the only ancient cultures that had a symbol for zero. If you're thinking of the positional system, you know that the zero term will have nothing to add, so the inclination is to simply skip it. But now, of course, if you have an empty space, you no longer know that you were supposed to actually skip a power, and you can confuse this by being one power too few, creating quite large mistakes, especially if your base is high as 20. Or in terms of Babylonians, for example, the base was 60, and a mistake like that on their part would have produced large mistakes. Now, Babylonians did not have a symbol for zero, and very few ancient cultures did, but Mayans did, and it proved to be quite useful in the very, very detailed and accurate calculations that they managed to carry over with respect to the solar system. This problem is, in a sense, a challenge problem, but again, will deepen your understanding of how systems across cultures and across bases actually connect. So the information you have is that a solution to a math problem in Maya numerals have one shell, 3 bars, and no dots. So the only symbols that we are working with here is a shell and 3 bars. Somehow these symbols were put together to represent a Hindu-Arabic 4-digit solutions. Okay? We are asked to write down all the possible solutions that actually fit these requirements. Now, because it's a base 20 system, we can already start thinking about what are the actual powers that we can work with. 20 to power 0 is 1, so this is certainly good enough. 20 to power 1 is 20, 20 to power 2 is 400, and moving up, we notice that the numbers here grow very quickly, and in fact, by the time we get to 20 to power 4, we're at 160,000, which is bigger than the 4-digit solution that we're asked to create. So this is already too high, which means that at most we can have this column of height 4. The only symbols we're allowed to use are these. Now the 3 bars, it doesn't say that they have to go together, so they could appear in different formats. So let's go through the possible variations. We could start with a shell and let's say all 3 bars in the same position. If you compute this number, you will notice that it is not a 4-digit solution. This is in fact too low for that. We could also have a shell here, maybe 2 bars here and 1 bar in the register above, and you get to figure out how low that is and go through all of the possibilities. So there's going to be, of course, some patterns, right? Like maybe I want to keep the shell at the bottom and then redistribute the bars as I can. But notice that because Mayans were aware of shell representing 0, I cannot have the case where, maybe I'll draw it so that it actually stays there. I can't have the case where I simply skip a spot and put the bar in the spot above. There has to actually be a symbol there. So this kind of situation is not allowed. They were also quite aware of the fact that shell as a sort of leading number was also not quite meaningful. So you cannot have the shell as being the top number with all the bars positioned below it. Same as we don't normally include leading zeros, like we don't say, oh, it's a number 123, but we write the 0 to be in the front. We simply don't do that, and neither did the Mayans. So this is also not allowed. Go through all of the allowable cases and see if you can actually find all the possible solutions for the 4-digit Hindu-Arabic numbers. Now, as an application to the actual number systems on the internet, we're going to see what the Internet Protocol version 4 and version 6 look like and how the binary numbers are used to represent addresses on the internet in another video.